Hello everyone, my name is Jianfeng. Today I will give you an introduction about our work FOAP, fine-grained open world Android app fingerprinting. Nowadays, mobile apps reshape modern lifestyles in different aspects. On one hand, mobile apps provide convenience to our life. On the other hand, they may also leak user privacy. Despite the widespread adoption of encrypted communication, mobile apps are still susceptible to app fingerprinting, which is a kind of traffic analysis technique. It infers user activity using features related to packet timing, packet direction, and packet size, without using packet payloads. It is a double-edged sword. Network administrators make use of it for censorship, malware detection, and user profiling. Attackers use it to spy on somebody or infer user privacy. There are two major limitations of existing app fingerprinting methods. Number one, they mainly work under the closed world assumption. The set of apps in testing must be a subset of apps for model training. Number two, existing app fingerprinting can only recognize apps of interest or identify some selected user actions. These user actions need to be manually labeled when constructing training dataset. In this work, we want to solve these two limitations. First, we carry out app fingerprinting in the open world setting. The major challenge is how to reduce the risk of false positives caused by app unseen during model training. Second, we want to achieve fine-grained user action identification. The major challenge is how to automatically label user actions to create training dataset. Here is the threat model. We assume that the adversary leaves network traffic on a wireless AP, and he can trace back all network flows to different devices according to the source destinations. The adversary wants to recognize user activities associated with app of interest, but he cannot use packet payload and destination feature of network flows. Our solution is called FOAP. Next, I will introduce the design of FOAP. Here is the overall workflow. Network traffic labeling module is used to create a training dataset. Traffic segmentation, traffic filtering, and flow recognition module work together to conduct open-world app traffic recognition. After that, method-level user action identification module will further carry out fine-grained app fingerprinting. To achieve open-world app traffic recognition, we need to create coarse-grained training data and label network flows with app package name. So we instrument socket-related functions of Android system and use PID to correlate the socket with app package name. For each flow, we extract a feature vector from different angles associated with package timing, package direction, and package size. Assuming that A is an app of interest, and we want to infer user activities about A. In the open world setting, the core task is excluding network workflows that are extremely similar to flows from A but not generated by A, because they may become false positives. To this end, we first propose a novel metric, local similarity. It is used to quantify how a network flow is similar to network flows generated by A from the perspective of a single flow. Network flows generated by A are expected to have a higher local similarity with A than those generated by other apps. So we can observe obvious difference between time periods dominated by A and those dominated by other apps. Based on this observation, we conduct traffic segmentation in an unsupervised manner to divide network traffic into different time periods, such that the APPA is active during some time periods. We formulate this problem as a computational optimization and propose a tree-based algorithm to solve it. The second step is traffic filtering. If the app of interest is active during a traffic segment, we refer to it as a relevant traffic segment. Otherwise, it is an irrelevant traffic segment, and we want to filter out it to reduce false positive risk. Based on flow pattern mining, we quantify how likely a network flow matches a certain pattern of network flows generated by A. Next, we compute the structural similarity for each traffic segment to judge whether flows in it match different patterns of the app of interest. A relevant traffic segment has high structural similarity with A because flows in it can match many different patterns, just like S1. On the contrary, an irrelevant traffic segment has a low structural similarity with A. It will be discarded without further analysis. Finally, we construct a bi-level recognition model to recognize network flows generated by A from S1. Next, we further identify fine-grained user actions from network flows generated by the app of interest. We propose master-level labeling to construct fine-grained training data. Generally speaking, there are three mainstream ways for Android to implement network operations. They are creating a new thread, using message handler, and using thread pool. We instrument different functions to map sockets to entry point methods, or EP methods for short. The EP method can be the component lifecycle or the UI callback. This EP methods trigger the corresponding network flows. To achieve master-level user action identification, we first extract packet bursts from network flows. It is because network flows corresponding to persistent connections often contain multiple packet bursts. They may be triggered by different EP methods. We extract a feature vector for each burst, just like what we do for network flows. Next, we construct a spatial temporal context model to characterize the correlation between bursts. We infer entry point methods based on conditional random fields model to identify fine-grained user actions, such as clicking on a button. Next, we evaluate FOAP. We first evaluate it in open-world app traffic recognition. We download 1,000 popular Android apps to construct a dataset. Experimental results show FOAP is reasonably accurate. Its F1 score is up to 0.911. It consistently outperforms baseline methods in terms of precision, recall, and F1 score. We also show the effect of different modules of FOAP. We can find traffic filtering helps improve the precision, and the bi-level recognition model helps improve the recall. We further evaluate FOAP in a more generalized open-world setting, including web traffic, IoT traffic, and PC traffic. The false positive rate of FOAP is very low. FOAP also achieves a good accuracy in entry point method identification. Its F1 score is up to 0.885. We also conduct cross-data set evaluation. We find FOAP trained based on traffic generated by automatic testing tools can still recognize traffic generated by human users with a high precision, but the recall drops. We also find adding some human-generated samples to the training dataset will significantly improve the recall. FOAP can be applied in fine-grained user activity inference. Here is an example of Twitter. We first correlate entry point methods with different user actions in Twitter. We next identify these user actions by identifying their corresponding entry point methods. FOAP can also be used to analyze user privacy. Here we show an example. In this example, we identify positive reporting in a COVID-19 contact tracing app. We evaluate how FOAP performs in face of countermeasure. The defense strategies include packet padding and dummy packet injection. Although the accuracy of FOAP drops, it still works. To summarize, FOAP is the first approach to identifying master-level fine-grained user action of Android apps. To this end, it reduces the false positive risks in the open world setting based on adaptive traffic filtering. To achieve master-level user action identification, FOAP synthesizes traffic analysis and binary analysis. Our method can be applied in user activity inference and user privacy analysis. Thanks so much for your listening.